Hi, I'm Julius. Welcome to my talk, a deep dive into MakieLayout. MakieLayout is the layout system for Makie.jl, which is a high-performance 2D and 3D data visualization package for Julia. So in the last couple months, MakieLayout was upgraded from a third-party extension package to an integral part of Makie's infrastructure. So now is a really good time to learn about some of the new features that we have to offer. There are a few common misconceptions about how layouts and figures work together and how you can tackle some of the harder problems when layouting. So I hope you learned something today and are inspired to give Makie a go for your next projects. So let's get started. Okay, let's have a look at how to build a figure from scratch, bit by bit, with the new syntax that was introduced when we merged MakieLayout into Makie, and also made the new figure object that ties all these approaches together. So let's make a figure, which is empty for now, and place a heat map into it at position 1, 1 in the grid. Here it goes. Then we can place a color bar next to that. And let's do another axis with lines. That's empty for now. We'll plot some lines into it. Here you can see the cycled colors, also a recent feature. And let's make a legend next to it. That's fine. Then we can do a mesh scatter plot in the next figure row, row 2, across the first 2 columns. There it goes. And an image plot next to it with this nice cow. Alright, so in Makie it's really easy to iteratively change things about these figures. For example, I can change the title of the axis with the image to image of a cow. There it goes. All of these things are interactive, so I can rotate plots and I can zoom into them like this, or I can zoom around and pan or select parts that I want and reset. Right. Other things that I can do is shift elements in the figure around. For example, I can assign the image axis to the place where the lines were before and shift the other parts down. It looks like this. So you see the axes here changed positions. I can also change parts of the layout itself. For example, I can make the first column wider, twice as wide in relation to the other column as it is now. So here you can see that everything shifted to the right. There's more space for the heat map now, which we can reset, of course. And I can also resize the whole figure, so you can see that the elements just follow, no matter what the figure size is. It's also really easy now to theme your plots in Makie. There are some themes that are provided. So for example, I can change the underlying theme to black. Nothing happened now because you have to actually replot. But here you go, everything is in a black and white theme now, which looks really nice. Right, that's how easy it is to build plots iteratively in Makie. And in the next parts, we're going to look at some deeper insights about grid layouts and how to place these widgets and axes into it, and how to style figures exactly how you need them. One of the most important features of grid layouts are the protrusions. These actually allow all the fancy alignments of objects that you can see in MakieLayout examples. So let's run this function protrusions. And here we can see that we have 9 grid layout cells, which are the orange ones. And the red rectangles around them, they fill the protrusions. So it's much easier to see when we change the size of the figure. So when we drag this around, you can see that the red areas stay at the same height or width relatively, while the inner parts, the orange parts, they can expand and contract. So the outer parts are the protrusions, the things sticking out into the gaps of the layout. So you can see the inner part is allowed to grow and shrink, and the outer part along this or this dimension always stays the same. And you can think of this, for example, as X-tick labels, this as a title, this as a side title, or Y-tick labels. So because objects are by default always aligned with their inner parts, that alleviates most of the layout issues that you know from other packages. One thing that is really useful about protrusions is that they work across nested grid layouts. Let's look at one example here. The top grid layout has 3 rows and 3 columns, and there are these axes like mock objects placed into that, where the protrusions are the red rectangles on the sides. You can see when I change the figure size that the protrusions always keep their relative width or height, and the inner parts are allowed to grow and shrink, just like axes. You can see that the 9 rectangles right here are part of a nested grid layout which covers the row 1 and 2 and the column 2 and 3. This grid layout has 3 rows again and 3 columns. And you can see that the axis objects at the sides also have protrusions going to the top and to the right. Now the important thing is that these protrusions, which could be titles or tick labels or what have you, are aligned correctly with the objects from the top level grid layout. So you can see that this line is perfectly straight all the way across, as is this line right here. This means that whatever your figure size is, all the objects across nested grid layouts are aligned correctly at their protrusions. Every layoutable object can either be placed in a grid layout to control its position, or you can specify a bounding box manually. So let's look at a manual case right here. We create a figure with an axis inside that has its bounding box specified manually. It's this particular rectangle. So whenever we click the button, this bounding box is set to a different random rectangle in the figure. So let's do this a couple of times, and you can see that the axis moves around and just takes the bounding box that you give it by chance. This can be used, for example, to specify inset axis positions, or whenever you feel you need a lot of manual control and a grid layout is not enough. That should be rare, but now you have the ability to do really special cases as well. Here you can see how figure and grid layout are actually decoupled objects. First we create a figure, and then we create a grid layout that has a manually specified bounding box with a size fit to the figure size. Then we create an axis, and notice that we don't place it in any particular position of the figure. We just add it to the figure. And you can see that it ends up in the lower left corner because that's the default position for any object. Now we can actually assign the axis to a slot of the grid layout. Notice that we didn't add the grid layout to the figure at all, it just exists. So once we add the axis, you can see that it takes a space that looks kind of correct in the figure. The border to the figure side was kind of looking nice. And here we do the same thing with another axis, which we add in another column left to the right of the other axis. And then we add another axis at the second row, just for good measure. So this looks correct, but now we can actually change the figure size, and you can see that these objects are not at all tied to the figure size how we're used to it. So that is because this grid layout just always sits at this bounding box position and doesn't care about the figure size at all. You can also see this when you look in the figure layout. You can see at the lower right that there's a grid layout with 0 children because we didn't assign anything to the figure's grid layout. We have a separate one right here. So what we can do now is assign the whole grid layout to the first cell of the figure layout. And once we do that, you can now see that everything snapped to the correct size of the figure. And when we drag it now, everything updates because our manually created grid layout is now controlled by the layout that the figure owns. And this changes the size together with the figure. So we can, as a last thing, look at the figure layout again. And now you can see that the upper grid layout has one child, which is our grid layout that itself has 3 children, which are the 3 axis objects. One misconception that comes up quite often is that a grid layout is like an array and that each layout cell is like an index slot of an array, which is not true, as we can see in this example. Here we have a grid layout with a button and a big box, and at each click of the button we add another box to the same layout cell that the gray one is already in. You can see this on the left. This is the bond that we already see, and this is the box that is created at each click. So when we click the button, there's a random box, there's another one, there's another one. So these boxes are scattered all over the place because their heights and widths are actually random, and their aligns are also random. They all occupy the same grid layout cell, so you see that it's very possible to add multiple objects to one cell. They just don't take the size of the cell because I set the size manually. But you can see that when I move this grid layout, all these boxes are moving inside the cell that they belong to. They don't change their size, as again that's set manually, but you see there's no problem with multiple objects being part of the same grid layout cell. We can actually look at the layout here, and you can see that all these boxes all occupy the same position in the grid layout. So again, a grid layout is not like an array. In this example, we can see how the attributes tellheight and tellwidth influence the size of objects in the figure. At the top, you can see a button that says tellheight on. So the row that it is in is exactly the size or the height of this button, because it tells the layout what its height is. When we click it and set it to tellheight off, you can see that the row expands because there's no object inside the row which would tell it which height to take, because there's only the button, but the button doesn't tell its height. So you can see that the upper row is exactly the same height as the second row. When we click the button again, the row shrinks because there's now again an object with a known height. The same goes for columns, so you can see that both axes have the same width, and there's this button here that says tellwidth off. So that means that its width is not included in the computation of the size of this column. So when we click it, you can see that the column has now shrunk to the width of the button, which might be too narrow if you want to see something in this axis. So usually in a case like this, you would set the button to tellwidth off so it doesn't shrink other content. But even if it's on tellwidth on, that doesn't mean that the axis has to be the size of the button, because we can also set the axis to something else than width is auto. So if we toggle the axis width to a fixed number, such as 400 in this case, you can see that the column has now expanded to the largest object in terms of width, which is the axis now and not the button. So you can see that now clicking tellwidth off or on doesn't influence the column size anymore, because there's a larger object inside it already. An issue that sometimes comes up is if elements are not aligned quite nicely in their default setting, in which case you sometimes need to change their align mode. Let's have a look at this example. We have 3 axes, and the one on the right has very long ticked labels. the one on the left doesn't have any tick labels at all at the bottom. So you can see that this results in wasted space here because both axes are aligned with their lower boundaries here. So you might think in order to get this space filled that you need to pull this axis down into the gap. But what you need to do is actually the opposite of that. You don't do anything with this axis at all, but you have to change the align mode of this axis right here. It's currently set to inside, which means that the inner layout cell is filled with the inner part of the object and the outer part of the object, which are the protrusions. So the title here, the decorations here, and the tick labels here, they are part of the gaps outside of the layout cell. So we don't want these labels here to be part of the gap. We want them to be part of the inner cell. So we need to change the mode from inside to mixed, where the bottom is like an outside align mode. For that we can switch the align mode here with this button. So now that we switched the align mode, you can see that the left axis has taken the space in the gap that was there before, and it's now aligned with the lower boundary of the tick labels here. The tick labels are actually part of the inner part of the cell now, which is exactly why we have solved the layout issue with the align mode. Mixed is a mixture of the inside align mode and the outside align mode, where the outside align mode has all four sides on the inner side of the layout cell. One part that uses this align mode by default is the very outer or the topmost layout of the figure. That is because you don't want any protrusions of your objects here to stick outside of the figure area. The value 0 here just means that there's no additional padding on the outside. And when we look at the align mode of the top layout, we can actually see that it has a padding of 16 by default, which is exactly this space that you see right here. One feature that's maybe not so obvious if you come from other packages, but is very useful to tweak your figures perfectly, is placing objects in protrusions. So I'll show that here with a new blank figure and some axes that I put into there. So let's say we want to group these upper two axes, each pair, with a label that goes along them on the right. So we can do that either in the standard way by placing a box and a label in their own column in this nested portion of the grid layout. And you can see there's a column gap here. But the other option that we have is to place such a thing into the right protrusion of the existing column. So the syntax for that is normal rows, column, and then the protrusion that you choose. In this case, right. So that looks like this. So now the same little assembly is part of the column gap, right? So we didn't make a new column, but it's part of the column gap. That's why this line is still aligned with the lower axis. And in this case, the right line is aligned with the lower axis because this is actually an own column, while this is just part of the gap. One point where this is very useful is when labeling axes. So you can see that I can easily place labels around this axis just by placing these labels into the different protrusions that are available. And this makes it really easy to label your subplots without them colliding with other stuff, because you can see the C, D, and E, they take their part here, their place in the gap, and they will always push stuff to the right that might be there in a more complex figure. You can even go further with this and place things like an axis in a protrusion, as long as you give them a constant width, because the protrusions are meant to be fixed size and not variable size like the normal content. So let's place an axis into the right protrusion of the lower left cell. Here it is. And just to demonstrate, we can actually plot into it. So you can get very creative with this technique and align objects in the grid exactly how you need them. In Makie, it's very simple to build large, complex figures out of reusable parts. Here's one example. We have a function myNestedSubplots, which places 3 axes in a layout. One axis at row 1, column 1, another axis at row 1, column 2, and a third axis in the third row and across both columns. Usually, you would think that F is a figure, but that doesn't have to be the case. It can also be a nested figure position. Let me show you what that means. So we create a figure at first, which is blank. Now let's place an axis into it at position row 1, column 1, just like we usually do. Here's that axis. So now if we call myNestedSubplots, we can give it a figure position, which is, in this case, row 1, column 2 of the top layout of the figure. So if we run this, we get a nested layout in row 1, column 2, which is this whole field. But inside there we have a nested layout where an axis is placed at the first row, first column, and so on. You can see that the objects belonging to the same layout have the same color here. Now we can call this function again, this time passing row 1, column 3. There you go, there's another nested layout, perfectly aligned with the others. You can see that there are 3 larger columns which have the same size, and there's actually just one large row. So let's do another call. This time we take row 2 of the upper layout with all 3 columns. So here's how that looks. You see it's the same sublayout, just stretched over a larger area. So you can see that we still deal with one top level layout and smaller sublayouts by actually changing the column and row sizes of the figure layout. So at first we can change the column size of column 2 to auto of 2. What that means is that the size is 2 times that of other auto-sized columns. So if we run this, you can see that the middle column just became 2 times as wide. We can also do the same thing with the row size. So for example, change the row size of row 2 to a fixed number of 400 units. So here you can see that row 2 with the blue sublayout became really large, and the rows at the top became squished because there's not much more space available. So in this way, it is really easy to write your nested subplot functions and then apply them for different locations in the layout. That's all for now. I hope I've given you a better understanding how the layout system in MakieLayout works and how you can make use of it in your own projects. I want to thank Simon, who built Makie from the ground up, as well as Pietro and Frederick, who have spent a lot of time fixing bugs, contributing code and ideas, and in Pietro's case, building Algebra of Graphics, a very sleek Grammar of Graphics plugin package built on Makie, which you should definitely check out. Thanks to all other community members and users who support us. Have a good JuliaCon and see you soon.